Hello, everyone. My name is Marco Jacoboni. I'm one of the faculty at the Brain Mapping Center, and I'm delighted to host this seminar. I've been a fan of Uri Hasson's work for many, many years. Indeed, I'll tell you the story how I discovered his work. I was keen in Telluride, and that was like almost 20 years ago. We didn't have smartphones. Our house we rented didn't have Wi-Fi. So I go to an internet cafe to check my emails every day before hitting the slopes. And one day I check the new papers in science. And I see Uri's paper on synchronized brains while watching movies, and it completely blew my mind. And he's doing things that blow my mind even more now. He's done his PhD with Rafi Malak at the Weizmann Institute. Then he, crossed the oceans and did his postdoc at NYU with David Higger. And then Princeton was smart enough to get him, and he never left Princeton, and he's done this beautiful work. And I'll just shut up here and let Uri talk.
So I'm very happy to be here. People on Zoom, because I like to move around, I will try to give a different angle. And let's see if I can get rid of this. All right. Okay. So I'm very happy to be here, and we're going to talk about a new line of research in my lab. Very new, and I want to start with basically, this is the most important slide. This is the people that did the work. I'm only presenting. It's really a big team. We have basically a collaboration between my lab and NYU Epileptic Center and people in Google. So it's really a big team. But I really want to mention Ariel. Ariel, basically, I think, is the driving force in this work. So he's basically leading most of it. Okay, I think we are stuck with this. Right? There's nothing we can do. Okay. So let's start. I just gave a class lectures in a class, and so the first two slides are going to be identical, the same origin point. The origin point, basically, we're all aware that there is like a replication crisis in psychology, in neuroscience, and in general in the sciences. But there is also another crisis. In this crisis, I'm telling it the logical validity crisis. And right, so last time. And basically, this crisis is not that we are failing to replicate results, even the results that are most replicable in the lab fail to transfer to real life content. So then we get to a situation that we really modeling our lab experiment instead of modeling the processes in psychology that we have. This is really problematic. And I think it's coming from the following reason. I think basically our lab experiment, we want it to be ideal. We want it to be simple, interpretable. A few parameters that have a lot of power, and we want it is like simple and interpretable parameters that we discover in the lab to be able to explain everything that's happening in the lab. Right? Because we don't want to explain the lab, we want to explain cognition in the wild. The problem is that when we go to this like ideal, simple and interpretable, our models fail to generalize, to explain real life. So this is the problem. And why it's happening, I think, I'm summarizing a lot of thinking, and I will try to make it more concrete when I go on. It's from the following two reasons. Real life are multidimensional, they are messy. Okay? So they are far from being ideal and simple. They are now, when I'm speaking, there is many intervening factors. What you ate in the morning, how much you slept, which newspaper you're reading, which scientific journals you're reading, which lab you are coming for, did you have a fight with your friend? This is all going to interfere with me speaking. So it's very multidimensional and messy. And it's also specific to context. Difficult to get to rules because in different contexts, and this is my responsibility, in different contexts, it's going to be slightly different. And our notion, we wanted like simple, interpretable, strong theories like physics, like Newton, four dimensions that explain a lot challenging psychology in neuroscience. And I'm going to give you an example of language. And then I'm going to give you an alternative way of doing science in the real life that can really come with a model to model cognition in the real life. And if we accept it as a cognitive model, it's a paradigm shift. So maybe most of you won't like it, because if I'm correct in this direction, it means that we need to change the way we are thinking about psychology. So it's really, there's a lot in stake of it, and this, therefore, I really want you also to interact and interfere and say, don't like it, please explain more and push me, and I will try to answer the question. Okay? So let's do it with language, because language is the basis of the cognitive revolution. Okay, and it's the basis of cognition. So what's happening in language? Language is complex and messy, right? And multidimensional. And we say what we want to understand it is a cognitive process. So what we are doing, basically, we try basically to look for the simple underlying ideal principles that can explain language in the wild. So we look at it as psychologists and linguistics, and we see some structure in language. It's not chaotic, right? So for example, we see there are part of speech, there are nouns, there are verbs, there are pronouns, there are adjectives, and then we see there is like some structural in language. And then we say this structure that we see in the stimuli, there's an underlying principles that are very simple and beautiful. Right? So we put that there's like this like underlying universal grammar. And then we define that rule-based system that is very simple and clear, by which we try to understand how language operates in the wild. And we also try to look what is the neural basis of this cognitive neuroscientist. And the problem is that this is very, very difficult to do. And in a way, it's not really working well. So first thing what we're trying to do is, oh, it's so complicated. Let's divide and conquer. Let's simplify. And this is where you go to the lab and simplify it even further. For example, in Chomsky, a classical example, he gives you this like sentence that has no meaning and says, I don't study meaning. I don't study pragmatic. So no semantic, no pragmatic. I study syntax. And this is the syntax. In the syntax, I will work. It will work. And I remove everything else. But even in like divide and conquer, simplify lab experiment, it's not working. And why it's not working? It's not working again because of context. It's not that it's a failure. Okay, let's say linguistic words and linguistic system manage to explain 50% of the situation. This is a lot. If change is zero and we start and you explain 50% of the cases, you are very happy. But it's only 50%. And why it's 50%? Because for each rule that you come in language, you have 50% exception. So let me give you an example. For plural, add the suffix s. Simple rule, right? Then you can see. But in some contexts, you have to add es. And in other contexts, you have to add is. In other contexts, you have to add vs. In other contexts, I don't know, it's irregular. Simply learn it. And then even if you learn all this like example, sub-rule, in regular strange context, you get to this thing that can definitely singular, and you have this s. Why? And that's basically true for each linguistic word that you have. And you know, and it gets more and more complicated. And then you cannot basically program your rules into a system that will work in real life. All this like endeavor of basically finding the structure of the ideal principles, it's failing in real life, really failing. And because context and the message. And suddenly, in the last 10 years, coming out of field, not us, very frustrating for us, I think, at least for me, I got very frustrated, comes like big models that suddenly work in real life. And I will show you how they are working in real life. And so first, we need to remember these models work in real life. They basically solve a problem that we fail to solve in cognitive neuroscience. But they are very different. And this is not our model. This is not what we love. This is not what we train off. We have very bad reactions. We call them black box. If you look at the number of parameters, there are 1.5 billion parameters. This is not a model of 5 parameters that is incredible. It's like monsters that trained from data. And we don't like them. And we're going first to explain to you how they are working. And then I will argue that they are not black box. And I think there's something that we can learn from them. But if we are learning from them, it's a paradigm shift. So let's start. To try to get rid of it?
Well, it won't let me disable the waiting room anymore. Must be a new feature. But can you stay closer to your laptop? They said the sound's better when you're closer.
Yeah, of course, it's better.
Yeah. Sorry.
And then you see my face. Okay, so I will try to stand over. Okay. So let's see. Let me explain. How many of you only to know the people in the Zoom I want to, how many know a lot about these like deep models? How they are working? How to but also the principle. So I'm going to give a very brief, very superficial introduction. Okay, if you want to, without math, without question, but I'll try to give you the intuition what they are and why they are interesting to cognition. And you are focused on language, but I can give the same talk in vision, and I can give the same talk in memory, and the same talk in motor learning. So that also tells you that it's general principle for cognition. Okay, but we're focusing on language in this talk. So let's see if I can go back. Okay. So first, to understand this model, you need to understand what is the vector-based representation. Embedding. This is Husserl. For each word, let's start with the simple case, and then we're going to complicate it a bit. This is the old model. You can vectorize language. Let's say you have, for each word in the lexicon, you have a vector of 50 numbers. Right, so now, suddenly language does become discrete, become continuous multidimensional. So I have 50 dimensional for each word. So all the words are sitting in 50-dimensional space. We start with random embedding. So we give like random number of 50 numbers, random 50 numbers to each word. When you give random, it means that all the words are going to be orthogonal to each other, more or less, because it's a big parameter space. And then you start to train a neural network. In this case, you have this, you take this like a 6 words, you mask the middle one, and you feed it to a neural network. And the neural networks get this like a, for each word you get 50 numbers. So you have a matrix of 50 by 5, and it's missing 1, 50 by 6, and you need basically to guess, and you multiply the matrices, it's random weights, right? So you start with random, you get random vector of 50 at the end. And you look, this random 50 is similar to a word. Of course, because it's random, you're going to give it like random vector, you get like junk, right? You won't get anything. And you say this basically after guessing, I'm guessing a word, predicted word, but I want it to be time because this is the solution is time. In this 1 second time, the word, right? So we wanted to predict time, but we predict junk. So now I'm changing basically, I have an error. I'm propagating back the weight to change the weight for next time to be closer to the word time. Okay, this is very simple recurrent. You do it for the entire internet, okay? And then you get a vector for each word that starts to get the structures of the language. For example, this is a classical example. If you do king minus man, you take the vector of king, subtract the vector of man, add the vector of woman, you get 3, right? In natural language, it will be like king to man is like woman to queen. Right? Because, basically, you can get other things. Basically, this is because we have Marcos, or we have like Rome to Italy, is like France to Paris, right? But you also start to see that you also capture some grammatical structure. Walk to walk is like play to play. So you start to learn things about it's multidimensional. It's not only semantic. Okay, we call it like word embedding, but it captures a lot of the dimension in the language. For example, whether you project it to feminine and masculine occupation, you can see the statistics. What is the association of occupation to feminism and masculinity, right? But this is the old model, not a good model. What's not good enough? Because if I'm taking the word in the lexicon, let's say I'm taking like one arbitrary word, cold, I'm getting like one vector for cold. But the word cold is going to change based on context. Remember, context is the key, right? Key. So for example, if I have the context, it is freezing cold today, or if I have you are a cold person, or if I have the cold symptom include, I'm using the word cold in different meaning, right? As a temperature, symptoms, or personality trait, right? So basically now you want that the vector code will be really effective by context. And look, context is even longer than a sentence. I'm giving you the sentence, you are cold as ice. I'm talking about your personality or about your temperature? You don't know. But if you will listen to the conversation, you will know, because it's more than one sentence. Context is long. Okay? So what they are doing in the new language model, basically, they do it with context. They take, it's self-supervised. That's really nice. It means that brains can use this trick as well, because you don't need anyone to program it. So what you are doing, you're taking the story and divide it into the context and then the next word. Okay? Now, basically, you know the answer, right? Reinforce, right? And you know the input. And now you have this like neural networks that's going to predict basically the next word, right? And you try to analyze the network. And we call it contextual embedding. So why it's different than basically the static embedding that I saw before? You start with static embedding. You start with the word vector as before. But now basically you can give up to 1,000 words. So you really give the entire context. But you give a long 1,000 words, it's almost like a document. In the new models, it's even 2,000 words, okay? And then you start to multiply this embedding, and at the end you get this like contextual embedding. So now this is an embedding that depends on all the words that came before. Okay? And from this embedding, basically now you try to predict all the words in the language. You have, let's say you have 50,000 words in the lexicon, you have 50,000 predictions. And now you can take you can order them by the top prediction. You can take the top prediction. And now you can compare it to what came actually. And now you have your error signal again. And you can backpropagate it and train your networks on the entire internet. So now you have a vector, contextual vector, that depends on the words that came before. It's not static anymore. And this is basically a different solution to that, basically. Instead of basically, let's see, once in a while, I was thinking we do it, that we do part of the process. Oh, okay. Okay. So instead of learning a rule, you learn that in this context, I got a pair. A pair is like a singular, but because it's pens, you use S. This is in this context. In other contexts, you can learn, you know, I bought colorful pencils. You use now the plural pencil. Similar, you can learn that moose, although it's like a plural, it without S, and elephants will be with S. Okay, you can simply learn the context. You don't try to learn generalized world. You try to learn how to behave in a context. And another thing that is strong about this like model is they become generative. After you train the model, you can chop the air and ask it to predict. So you have the sentence, I bought a pair of, the model predicts pens. Then you can plug pens back in, and also predict the next word. And now you can start to generate new text. And you can all type. There's like apps in the web that you can talk with this model. So to save time, I gave you an example. We took an article. This is the article. Okay, Pelosi predict vote for Biden bill that actually failed. Her prediction was wrong, but basically that was our prediction, and there was an article. We chopped the article. We only gave the title of the article to GPT-2, and say this is the input. Generate a fake article. So the model generates a fake article. Okay. So this is the output, and this is what you're saying. Now that you read it, you can see how good is this like model. Basically, look, first, you can see that you know grammar. You have no mistakes in grammar. So you basically learn grammar. But then you can also see he's speaking on the topic. So he's talking about as Democratic leader Nancy Pelosi try to, with moderate Republicans. How you know that he's working with moderate Republicans? You know a lot, right? So you know about the topic. You also have pragmatic, you fake it like source. You know that it's like this like newspaper style. So you have a fake of this style of newspapers with quote. If you will plug in scientific abstract, you will talk like a scientist. We do like a references, Smith et al, and we fake the references. So you really know the pragmatic. You have word knowledge, you know who is Nancy Pelosi because you read a lot about it. And common sense, it's not like a perfect. Also, it's like empty sentences. If you read, I cannot guarantee you it will pass, but I can guarantee that there will be the vote. So it sounds like an empty sentence. Also, politicians talk a lot with empty sentences. It might be like mimicking the statistics, but this is a good language model, right? It's not like a bad language model. You know a lot. Working in real life, this is what we wanted to do with our models. And now people from OpenAI and Google and Facebook coming with these models, that in a way, we're feeling uncomfortable with it, right? So now we can ask, and this is the question of this lecture. We have two opposing, what do I say, fully developed. It's basically, we have models that are working. The classical models are working. It's difficult to program them. They're working 50% of the time. They're very clunky. It's very difficult really to program all this like exceptions and weirdness into them. But we have something that working 50% of the time. And now we have something that's working even better, but both of them are working models, okay? So now the question we always ask in science, which model is better related to the brain? And I want to be clear. I'm not an linguistic, and I'm not an engineer in Google. I don't care about either. I only care about the brain, what the brain is implementing, okay? And the question that we're asking ourselves in science all the time is which model better fit what the brain is doing? Okay, so now we have a model comparison problem. And when you frame it that way, you start to ask, how do you start to answer about this like 1.5 billion black box parameters model? Is it really relevant or not? How do you start this like line of research? So first is, I understand two things. First is it's a family of models, okay? It's not basically that there's like one solution to do it. This like a transformer-based model that I gave you, it's one implementation. There are many ways to implement it. And there's also many ways to write this like rule-based model. So we're asking whether the brain is related to this like family of model or this family of models. It's not that it's transformer. That would be really silly because we know basically that the brain implements it in a very different way. So we are not asking about the actual implementation, we're asking about the computational principle. Why this model is working? What are the computational principles by which it's working? Okay. So basically, I'm going to present you 1.5 work and then some future direction. There is a lot that is going on in the lab. We're writing 4 new papers about it. I won't be able to cover all of them, but it's really a rich research program. We're only at the beginning, so I won't give you the final answer. I will give you how we are going about it, okay? And we're going to tell you about computational principles between these like deep language models and the way our brain processes language. And also we'll talk about some differences between the way we process it and implement it than the way these models, and how we can make them more psychological oriented, okay? So it's going to be like a mix, but I think this is the family of models we should pay attention to. And don't say they are out of the field, they are not related. Any questions before I'm starting? That was only the introduction. Oh my God. Okay, so let's go to science. We took a story, a 30-minute podcast, okay? We can fit this like a narrative into the language model. We use GPT-2, okay? And we can get basically the embedding from the model. We can get all the prediction, and we can get the error term, okay? So now we know how GPT-2 is going to process this story. This is how our model processes the story. Now we also can give this story to ECoG patients, so we can record their brain activity, and we can see how they process the story. And I will show you basically that similar to GPT-2, they code language. Oh yeah, I think that basically all expert in. Okay, so basically ECoG basically epileptic patients to locate their epileptic source, they go invasive procedure, they open the scalp, they put in electrode on the brain for a week, trying to see where is the seizure coming from. And sometimes they are willing to do experiments. In our case, it's easy because they simply, it's not an experiment, they listen to a podcast, enjoy it, and you get their brain responsive. And it's really invasive, so you get really a view into the internal processing of the brain doing its natural stimuli. So it's very rare and beautiful data to it. And we are very thankful for it. So basically, we're going to show you that the brain uses contextual embedding to represent language. I'm going to show you that the brain predicts for each word before it's coming. They have a prediction. And then after you're listening, you have an error term. So in a way, basically, you can see that the brain implements this like objective function also, like it's like deep neural network. So this is the shared principle I'm going to show you. Okay. We have this like neural activity, we have the sound wave, we have the word. And now for each word, we can give an embedding. Okay. We can give an arbitrary embedding, so it's like a random number of 50 values. We can have the word embedding, the static one that I saw before, or we can give the contextual embedding. We do encoding. How many of you know encoding? I need to explain encoding over here. Encoding, basically, you try to find a mapping between your 50 dimensions and the neural responses. So we have a model that learns from 80% of the data, the transformation, and then you test it on and use that 20% that you left out. Okay, so it's like a linear model. Okay, and basically, so we try to predict the neural activity for 20% of the world that we've never seen before, and we compare it to the actual activity, and we know how good our model to predict the brain activity for this particular words. And remember also, this is something that is really important. This is real life. So in a way, we're asking whether this is a model to study real life responses, right? Because we don't other way I can know how you represent to a word in a story, right? It's a very difficult problem we are dealing with. We try to have a model for arbitrary story that we took from NPR. Anyway, it's a very challenging task, right? What we're asking. So basically, if if you take an arbitrary embedding, in a way what you are searching, we're saying that it will be consistent activity pattern for a word. Let's say you say the word monkey twice. You want to learn from this particular example of monkey how the pattern will be for the 20 times you use the word monkey. And this model is working, okay? You have some consistent activity for language. But if you use the static embedding that start to know it's the same dimension, 50 dimensions, but now you rotate it to capture the geometry of language, of the word meaning, like queen to king, you start to get way better model. And if you go into this like new contextual embedding, it's even way better model. So you can see that this model start to capture the way we represent words in natural language. You can see that this is a very strong response. We have some electrodes that have correlation of 0.4, which is like really good prediction, right, of neural activity. So we really get good prediction from these models. Highly significant, but also very good. Next, we say, then we look on the brain embedding themselves. We have like 4 subjects that we have a very dense ECoG grid on Broca's area. Okay? So this is the language area. So now we have 81 electrodes located in language area. And this, basically 81 electrodes give you like 81 dimension brain embedding. So now for each word, I have a vector of 81 electrodes. So now I have a brain embedding for each word, okay? And now I also have the language model embedding for this word. I do some PCA to reduce them to lower dimension, okay? So now basically, let's say I have the dimension of the GPT-2 and the dimension of the brain embedding. I can use 80% of the data to rotate. So I can do alignment. Okay, and now I'm taking new words that never seen and ask, can I know what is the brain embedding from them based on the brain embedding from the language? So I'm asking whether it's really the brain used, whether language areas really use this like brain embedding in the same geometrical space. Okay, because it's like zero sum. You never seen the word code. You only, or the word weak. You only train on the blue ones. And now you try to predict completely new words that you never seen before. So it's really whether you can really generalize to a new set of words you never seen before. This is called zero sum in machine learning. And basically, why did I get that? Something went on. Oh, I lost my presentation. It's cursed. Sorry. Okay, it's going up.
Stop the screen share and then start.
Yeah, maybe I need that to go. I was over there. Yeah, okay. I need to present. And now, it's okay?
And then just get rid of the toolbar.
Okay. If someone doesn't see it from the Zoom, let us know. If it's working, it's working. Okay. So basically, you can see that we can really do zero sum prediction for new words that never seen before. And these words are better basically than words that were in the training set. For example, if we had like baboon as a word, it's really interpreted to baboon better to interpret to the monkey, which is the nearest neighbor during the training. So it's really managed to predict new words never seen before. Okay, so that's like really strong demonstration that the brain really used this basically embedding space. And if you go outside of the language areas to a nearby area, you see nothing. It's very specific to the way language areas code this type of word, very specific. Okay, and we see it for the different individual subjects as well. So for each individual subject, we can do the same analysis. So it's a very strong design. So we see that the brain represents language using this like high-dimensional embedding, which with very similar geometry to what we see in language. Next, we wanted to see, can they also basically do this like prediction, like GPT-2? So, for basically in GPT-2, before I'm saying each word, you predict what I'm going to say, and then you listen to me, and you get an error term. I mean that all the time, GPT-2 is do prediction in order to learn. This is the trick. The trick is saying that next word prediction is enough to learn everything about language. It's enough to learn the grammar, the syntax, the semantic, the pragmatic. It's a very good objective function. But we don't have a proof that the brain is doing this like a prediction in real life. So first we ask, how good are people to predict stuff? So we went to MTurk, and we asked the MTurk here to be like GPT-2. We are okay, get this sentence, can you predict the next word, type your prediction. And then I'm going to give you the answer, and then predict the next word, and then predict the next word. So now we have like 50 people in MTurk. We get 50 predictions for each word in the story. Okay, we have 5,000 words, we have 5,000 predictions. Okay, this is how it looks like. You have some words like the one on top in blue. Everyone knows what this word is coming, all the 50. Okay, you have some words that no one can predict. Okay, and then you have words that was predicted 80% of the time, or 50% of the time. So you have everything. And now we can ask, are your prediction as subject are similar to the prediction of GPT? Okay, and yes, the correlation was 0.8. So your prediction as humans are very similar to the prediction GPT-2 is doing. So we are also very good in predicting in real life context. Next, we ask, and this is basically, you can see it over there, the same. This is the result I showed you before. You can see that basically, if you're looking on the brain, you can see that GPT-2 is better predicting the brain responses than basically the contextual embedding, the static embedding or the arbitrary embedding, right? But you already see it over there in the results. You can see, look how much of the prediction we have before the word was saying. All these things happening. This is the moment. This is when the mind is the model on time zero when you listen to the word. See how much the model is doing well in predicting words before you're already listening. So I can really predict from your brain responses to the specific word before you even listen to it. So there is really evidence for prediction in the brain. And then we ask, can we go even closer? So you have words that you're really good in prediction. You have words that you can really never predict. Eye closed and low closed. So if we separate it, you can see that the word that you're really good in prediction, it's easier to read it from the brain before than the word that you fail to predict. Okay? So I can really see the quality of your prediction in the brain response. Now, another case study that we can do, and we see it in many areas. Okay? Another thing we can do basically is thinking about the error, right? How much surprise you are, right? So now over here, in this particular example, our story begins in the deep, in there. Most people, actually, our story predicting the deep, I'm missing the deep over there. Most people think deep ocean, but you hear deep rainforest. So your prediction was slightly lower than expected. Right? So you have some error rate. So I can take the word ocean and use it to predict the brain, or I can take the word rainforest, what you actually have. So if I'm taking the word what you basically were predicted, you predicted ocean, you get this response. You're thinking this is what basically the model predicted, and it's better to explain your responses before. And this is what you actually heard. And if I take in this model, it's better to explain it after you listen to it. So this is also a nice example that the brain always predicts before. And then we can ask, okay, so what about your error, right? You have an error then. So we can see the more error you have, the greater activity you have afterward answer. So this is the end parameter. So we can look on the certainty of your prediction before, and this is explained really, or the entropy, this is the So pilot level, and you can see that the level of certainty of our prediction explained way better before, and the level of error explained way better after. So basically, this is what we see the resemblance between these like deep language models and the way we communicate language. So now, for the rest of my talk, I have like few minutes. I want basically to give you also where it doesn't fit. So remember, basically, our task is to ask which model is better. And you remember that model is never the phenomenon itself. For example, is electrical car is a good model for a gasoline car? Yes and no, right? It's never going to be simple answer. Basically, is a bird, airplane is a good model for our bird fly? Even less so, right? So the question is never whether your model is perfect, whether it like captures more of the process, right? That is what we are asking. Which model is capture better what the brain is doing? So now we can also ask, where is the model failing? And how we can improve it to make it, if it's a real framework, and to how the brain is working, we need also to modify this framework a bit. So for example, GPT-2, basically you have different layers, right? So you start with static embedding, and then you have different layers that compute it till you get to the last layer that do this like prediction, right? So your model is, but basically you feed all the words at once, right? You feed 1,000 words, and you start to multiply it over time, over space. But we cannot do it. You have to listen to me word by word by word by word. You don't get this like 1,000 words at the same time. This is weird, right? So we started to look which layer fit better the neural activity in the brain. And what we discovered is really, it's a phenomenon basically. Remember, this is a computation now that the brain is going layer by layer. Layer, then you multiply with this layer. You take this vector, you multiply it with your nonlinear weight to get this layer. You get this activation, you multiply it to get this activation, this activation, this activation. Now we're going into the computation of the model. This is the actual computation the model is doing. And we're using each layer as a model. And we see that the brain goes to the same state of computation, basically, but it's going over time. Okay, so basically, you look in Broca area, and you can see that the first layer explained activation earlier, and then you move to the other layers, you can see really that it really goes over time. You can see a linear increase in the activity. And we see it also in different languages, but we see that the time scale is getting longer and longer, so it gets wider and wider. And this is related to the time scales I was talking about in the previous lecture. So it's really, look at this one even captures the internal computation of the language system. And that's, but it implemented it in a recurrent way and not in a parallel way. So it's different implementation to the same principal computation. And this starts to be weird, right? Because you get into this like internal model and say, why the way GPT-2 multiply matrices will be similar to the way Broca areas multiply the brain embedding. It's really, the connection is deeper than we are thinking. But also it's different. So for example, we calculate how much human hour it will take GPT-2 to train. So we say, let's say you can read 150 words a minute. We calculate how many words GPT-2 is seeing. It will take you 120 years of human life without sleeping and eating to train. We look on GPT-3, it will take you 6,000 years of life to read what GPT-3 is reading. So babies learn to speak without reading anything. So this is one example to say, okay, this is not cognitively feasible, right? Another thing is the model can see the sentence, how much time left to the stock, right? But I'm asking, how much time? Oh, it's 11:45. So there's grounding, like there's like multimodal, there's all this like psychological thing. You never learn the meaning of words from other words. You learn the meaning of words, how they are connected, what we are doing, right? So this is also different. So in a way, we'll have a multi-learning system. We have grounding system. We learn from embodiment from other people. We don't learn from reading the internet. We learn from other people. We're also thinking. This model do not think, they are echoing the statistics. Sometimes I'm thinking that most of us sometimes don't think because they see how much nonsense there are in the world and people say such weird stuff. So maybe we're also echoing the New York Times and Fox News instead of thinking. But we're also thinking sometimes, right? This model never thinks, right? This model doesn't have symbolic representation. There are continuous vectors. There's no symbolic representation. We want it to be slightly symbolic, I guess. You don't want to learn calculus from examples. You want to understand the rules. So there is something more to cognition than only this model. So we started to think, how can we make them more psychologically relevant? And this is where we are leaving the engineers in Google and start to develop our own line of research, right? Because they don't care about how humans work, they work about their product. So we're saying, can we train language models from human-centric perspective and not from this like textual internet? So there is this like amazing project by Dave Royal. I'm not sure how many of you know of this project. He wired his house with cameras and monitor his first years of his baby for 2 years, for the entire 2 years. But he did it many years ago. The data is not available for anyone, and not much came out of it because before machine learning, he failed to penetrate the data in a way. So we say, can we replicate his study at scale with new AI tools? So basically now, we are wiring 20 families in Princeton for 3 years with cameras. Okay, basically we have many cameras and microphones in each room. We record them for 3 years. The data is go automatically to the cloud without no human intervention, and basically we are now finishing building it, and it automatically analyze and store. This is an example I need of 1 hour. Okay, I cannot show you the identity, so I blurred it, but it's really happening now. And in 3 years, we will have the data. Okay, and this is an example. For example, this is not a real family. This is doing our testing. You can see they are playing with the baby. We detect whether there is a baby. We have a baby classifier. We see that there is a baby. If there is a baby, we process it. We do like automatic segmentation of all the body because we care about the embodiment. Okay. We take all the labeling of the house. Okay. We're running transcription tools.
Oh, I think she wants to flip. Yeah. Oh, yes, she did.
For the first time in this movie. Like, and now basically that we have this like we're going to have the data. You can ask why are we doing this like crazy real life recording? The point is that we can really now try to train. We won't do thinking and symbolic, but we can really now have all the information to train a language model from the child's perspective. We want to see whether we can make these models really more a model for our people learn. Okay, so this is basically what we're doing now. And it's a big project. I'm not sure whether it will fail and we are wasting our time, but we felt that if we really take this serious as a cognitive framework, we need to push ourselves and not stay with this like company that doesn't care about cognition and humans. But the beauty about this model is that they are context-based and they are memory-based. In a way, they can really be used by the brain to do cognition. But if this is the case, then we should stop thinking about our control experiment and the thing that will give us the answer, because it's a very different answer than the answer we are looking for now in cognitive neuroscience. So I'm not sure whether it will work or not, but that's what we are trying. And I think I will end over here. Yeah, okay.
Okay, some practical issue. We're doing a live thing, results of people on Zoom. So do we Can we check whether there are questions in the chat?
Don't have any questions in the chat yet.
Okay, good. Okay, I see your hands up. Good.
Great talk. Not sure. I, for the last portion, I don't know if you have models in Wix yet, but would it be some sort of reinforcement learning model that you would be like implementing?
Yeah, basically modeling it is going to be very challenging. We will need to develop the model has to be multimodal. They have to be grounded with the behavior. They have to be learned from the mother or the caregiver that's interacting. So there's social learning, there's moment of learning. For example, GPT-2 already have a lexical of 50,000 words. The baby has 0 lexical. So you also need basically to learn the lexicon first and then start to do this like next word prediction trick. So there is like also stages of learning. And we're really developing now new protocols for learning these models. It's very challenging. We're developing ideas, but to tell you that we know how we're going to do it and what will work, it's really early days. So I will say in 5 years, I will have maybe model that's working. That's the time scale that I see for this project.
Luciana?
Okay. Hi, thanks. What an exciting project. Can't wait to see the results in 2 years. But I was curious if you know of the developmental psych folks who are doing head-mounted cameras.
In Stanford, yeah, of course, you might find. Yeah.
So my question about the
Linda.
perspective, like, do you think it's important to have the baby perspective for making these models because that's what the baby's actually experiencing?
Yeah, absolutely. We are forced to stay with the third view perspective because I cannot have mount camera for 3 years of the baby, and I want the 3 years. I want the entire statistics. Basically, we have a lot of assumptions about language. Somebody was saying input is not enough. Parent doesn't give you supervision, therefore you have to have in 8 systems. This models say very weak supervision, yes or no, but give a lot of data and examples, we will learn. So we need to collect everything. So mount camera won't work. We hope that this third view will be sufficient, but you're right, also there is a limitation and maybe it will be great limitation. If I can recall all the sensory system of the baby, what it gets, and the camera, and the sound from his perspective, that's what I want.
Right, but this camera will pick up things the baby won't pick up. So.
Yeah, so it's good for us to know the context, so we get also the parent's perspective, which might be good. I think in the best scenario, you have the third view to know the context, and have the first view to get the input. That's what we really want, and we don't get it in this project. Yeah.
Just a follow-up. So you could actually estimate what the baby sees.
Yeah, we got that. Because we have a few cameras in the room and we want to reconstruct them. We know the rooms well for 3 years, so we want to do some estimation. We did calculation that we need like 8 cameras to do very precise estimation, and we have only 2 cameras, so the estimation won't be as good, but we will try to estimate.
I got a question from the chat. What was the self-supervised learning rule? Was it related to biology?
Oh yeah, we have a paper a theoretical paper that compare basically deep learning and evolution. If you think about evolution, it's optimization problem. There is no God, right? And the eye basically have to come with a solution without understanding the problem of vision or the solution of vision. And this is an optimization that we do across generation. Deep learning is also an optimization problem, right? You have an objective function that it's more than survive, right? In evolution, right? You have an objective function like get, eat, drink, or predict the next word, whatever your prediction, or recognize a face, and you use it in order to optimize the network. So now the question becomes, which our objective functions are really related to psychology? We saw that the next word prediction that is really effective for language modeling can be done by the brain because it's self-supervised. So this is a biologically relevant objective function. But there might be also other objective functions that relate to language. We don't think it's the only one. And if you take it as a family of models, what of the line of research that people need to take is what are the objective functions that are biologically relevant for humans and what are not. And if it's not relevant to humans, it should not be used by the brain. But there are many objective functions, like mirror neurons, for example, can be really a good objective for learning. I can imitate people as an objective to get ideas what to do. Right? So there can be many relevant objective functions to biology and psychology that we need to explore.
May continue then. Was that error backprop? Was it still an error backpropagation, or is it some other? Because you said it's self-supervised, so that's not error backpropagation, right?
Yeah.
Or was it?
Don't confuse objective function and the learning rules are different. Basically,
What was the learning rule then?
So backpropagation, only to be a bit technical, is the way basically you implement the learning rule. And backpropagation is not biologically feasible.
Right.
So now if it's similar to the transformer that it's not biologically feasible as an implementation of this like parallelized multiplication factor. There is a lot of work going on to find local learning rules, because the learning rule in the brain have to be local. We don't think that you project it all the way down. Local learning rules will be as effective as backpropagation, which is not biologically feasible. And that's why I'm saying it's the same family of models. If you believe in family of models, now you have to find the relevant implementation that the brain uses for biological neural networks that is different than artificial neural networks. So that's why we're talking about computational principles. And learning rule is a principle. How it's implemented, it has to be discovered.
Thank you.
I do have a question for you. One of your recent papers talks about this stuff, making an analogy with the ecological psychology of Gibson, which I think is illuminating. Can you elaborate on that?
Yeah, I'm not sure how many of you know, because it basically got forgotten from psychology. I'm not sure whether you're even is part of your training now, the young generation. You only have to remember Gibson. Basically, Gibson was talking about like direct perception. Basically, he was saying you fit to the dimension relevant to your action, and you learn it without basically doing this like representation, computational process. People say it's not like magic. What do you mean direct? You need to explain the computation. If you think about this, like this model, the model that acts in the world, basically they have an objective to act, for example, to open a face, or to eat, if it's a motor system, and to pick up stuff and eat, or walk, or predict the next word. They are acting or driving a car. So they have embodiment and action-based, that optimization without understanding the problem, because the optimization problem, learn how to act. And in a way, it's really linked to the way Gibson was thinking about the cognitive system as an action system that acts in the world without doing this like representation computation that people believe in psychology. So there is a strong link between Gibson and this like deep neural networks. There are also differences that we can talk about. Gibson was against memory, and these models are all about memory in context. So in a way, there are also some differences. But yeah, there is a lot of similarities. Right? It's really nice to connect it to a line of psychology that was basically forgotten.
One more. Oh,
yeah. Well,
yeah, I was just wondering, so like it seems like these models are really valuable in illuminating computational principles. Do you think eventually we'll also gain like neurobiological insight? Like for instance, with the recurrent architectures, those kind of seem to be working with the brain does, but they're not able to achieve the same performance. Do you think we can take those models and like improve them somehow and have some that's biologically possible?
Yes, absolutely. So basically, this is what basically we are doing. If you look over basically this, it's really there is basically, I think it's going to be a two-way line of result. Basically, if we are thinking that the same family of models, there is basically we can learn from artificial neural networks, and artificial neural networks can learn from the biological neural networks. So it's going to be a two-way line of research. Currently, in this particular project, we are taking the language model, the artificial one, and see that they are really valuable. So we need to start somewhere and change the paradigm. But you know, we are way more efficient network. You can think about us like version 1000, and Google version is version 1, because we went to evolution to optimize the network. So there's a lot. Google really want to learn from us how the brain is so efficient in learning, and because we are a more efficient learner. We don't need 6,000 years of reading to understand stuff, right? So they can learn from us. For example, the backpropagation stuff. Probably we have a better trick to do this, like learning and changing the weights, optimizing the weight. So they can learn from us, and we can learn from them. So I think that's going to be back and forward. It's in the case that these like neural networks were invented by psychologists, got forgotten, right? And then emerged again in computer science, and now they're going back to psychology and science. So there's like a feedback loop over there from the origin that will be interesting to follow. If we are right, if we are wrong, forget about my talk and keep doing what you're doing in the lab. So, you know, I'm not saying that even we are right. If this direction is correct, then that's what.
Yeah, thank you so much for the talk. I really enjoyed your discussion of how narrative context can help you predict like the next word of narrative. And I was wondering if you consider the context of the person, like for example, if they're angry or sad or hungry, it may be more broader than experience of what they're experiencing and how that would explain variability in their narrative interpretation of the next word.
Yeah, so it's also related to the talk I gave about who you are and what you bring to the table. Remember, this is context. If you didn't eat, this is context. If you have a fight with your partner before, this is the context. If you had a paper or a chocolate, so this, because it's contextual, you can view all these parameters as additional contextual factors. It's multidimensional, so they can really take these factors in. Currently, in language models, they take the factors, but you were saying words that related to your being upset somewhere in like 1,000 words before. But if you will make them more biological, I can also monitoring your emotional system, right, and your attentional system as a factor. But there, it's all context, and this is why it's easy basically to give them body and expand them to this like embodiment, because they're already like immersed in the world and contextual. So it's very easy to make them more biologically relevant and psychologically relevant than people think. People think, no, they are black box engineering. They have nothing to do with us. We really have strong aversion for them now in neuroscience. Or maybe I'm wrong and people already like started to like them. I don't know. I cannot read. How many in the audience like this model? So the cognitive framework.
Well, it looks like the younger generations even like them.
Yeah, maybe it's also a generational thing, because
I have a real question about the embedding.
Yeah.
So it's categorical embedding from words to numbers.
Yeah.
And there's probably only few limited ways you can actually do it. And that's fixed at the beginning.
What do you mean limited way?
Mapping continuous values to numbers is probably easier than mapping categories to numbers. Is that?
It's so basically, in a way, this is the trick, because you take like a symbolic system and you make it continuous, which is like really counterintuitive to language, right? Because we always think about language as categorical. And this is the trick and the magic. And vectorizing language, this is why the word of vec, the initial stuff, was like a break point that people say, why you can vectorize language and do operations, simple operations with language? How can it come? And we didn't expect it to be a full-blown language system, as we see in the new models, like that there are no pragmatic syntax and so it really is vectorized, multidimensional, is amazing. And I think why it's working, why you ask yourself, why is that like embedding space that GPT-2 is finding similar to my embedding space as human? It's very weird, right? But once you realize that actually this is a statistical model that fit to how people use language in the world, and this will go again back to Gibson, this is like basically embodiment of language. They fit to how people use words, and the baby fit to how the people use the words in the language, and this is why we get the same representation and the similar representation. It's not identical. I still think that this is an objective function to make it more human-like, but this is the trick. So it's really.
So my question was the process of embedding and the input, and then review the backpropagation and the final embedding.
Yeah.
At the input, say, it's not important. You could actually start any embedding. Or are we limited by the initial choice or the initial process?
Basically, there are two types of language. Now we get technical. Some people start with some models start with static word to vec, and some let it to learn end to end. But even and then the final product, you get static embedding at the beginning, and static embedding at the end, and contextual embedding layer one before. So they all convert to the same embedding space because they fit to the same statistics. It doesn't matter if you start with random. I'm not sure whether it answered. But yeah.
Also, you two are going to meet tomorrow, so, and tonight too.
Yeah.
Anyway, we should wrap it up. Thank you very much.